So we've started to look at hypothesis testing for two proportions, eventually two populations with the mean later on in the next section. So this section looks at paired samples for two means. So, the questions we want to think about, are two populations the same? Is the average height of men taller than the average height of women? Is the weight of college freshmen less after a diet than before, right? So these are two different types. One's independent, one's dependent. One way to compare populations is by comparing the means, right? So we're looking at the means. You take a sample from each population and compare the statistics. Anytime you compare two populations, you need to know if the samples are independent or dependent, right? That's the biggest thing here. So the formulas you will use differ based on the type of relationship between samples. If you choose one sample, right, has no effect on the way you choose the other sample, the two samples we say are independent. The way to think about that is, in independent samples, the individuals from one sample are overall different from the individuals from the other sample. This will mean that sample 1 has no effect on sample 2. The sample values from one sample are not related or paired with values from the other sample. So, the height of men and women, those would be independent samples. Now, if you choose a sample so that a measurement in one sample is paired with a measurement from the other sample, the samples are dependent. Sometimes they're called matched or paired. So dependent. And it's often a before and after situation. So, you could take they could look at your cholesterol level, you take some type of pill, and then they measure your cholesterol level again, right, to sort of see has it changed. So you want to make sure that there is a meaning for pairing data values from one sample with a specific data value from the other sample. One way to think about this is that in dependent samples, the individuals from one sample are the same individuals from the other sample, though there can be other reasons to pair values. This makes the sample values from each sample paired. So what we're going to do is just look at our first example, trying to determine does this data come from independent or dependent or matched paired samples. So A says comparing the incomes of 40 Democrats and 70 Republicans, right? These really are not matched together, right? They should be independent samples. So I'll just put independent. Then it says, B says comparing the LDL cholesterol for 50 soccer players and 50 basketball players, right? And these really should come from two different populations, right? We have our soccer players over here, our basketball players over here. It's not really a before or after in terms of comparing the cholesterol. So this would also be independent. Okay. C says comparing how many hours 70 students spend studying per week to how many hours they spend on their smartphones per week. So we have 70 students, right? So we look at how many hours they spend on their smartphone and how many hours they spend studying. But we're looking at the same 70 students. So this one would be called a matched pair or dependent, right? Example, so matched pairs. Because you're only looking at 70 students, you're just looking at different pieces. So D says comparing the days hibernated by 45 black bears in California and 45 polar bears in Alaska. Again, this would be another example of independent samples. Okay, so hopefully going through these examples just sort of gives you an idea of how you can tell the difference between whether it's independent or dependent. And again, we'll have different ways we sort of go through and do a hypothesis test for these. So let's take a look at this. So a hypothesis test for two sample paired t-test. So it's a t-test in this case. So the data for the test are the differences between the before and after for each individual in the sample. We will then calculate the sample mean difference, so x bar sub d, and the sample standard deviation of the differences s sub d, and test the hypothesis exactly as you would in a one sample t-test. So this is important because that's what we're going to use on our calculator. The degrees of freedom for the test are n minus 1, where n is the sample size or the number of pairs of data. So for my null hypothesis, right, so H naught, we have So mu, and we say the difference in the mean, we say is equal to 0. Okay. For my alternative, right, again, we see sort of 4 options here. Sorry, 3 options. But the same options we saw last time, right? So mu sub d is not equal to 0. Mu sub d is greater than 0. And mu sub d is less than 0. So two-tailed greater than, right, is right-tailed. And less than is left-tailed. Okay. And we'll talk a little bit more about how we sort of know, because it's the difference between them. So we're going to talk about, do we want an overall positive or negative difference to determine sort of the alternative. So we want to state and check the assumptions for the hypothesis test. So A says a random sample of n pairs is taken. B, it says the population of the difference between random variables is normally distributed, right? In this case, the population you are interested in has to do with the differences that you find. It does not matter if each random variable is normally distributed. It is only important if the differences you find are normally distributed. Just as before, the t-test is fairly robust to the assumption if the sample size is large. This means that if this assumption isn't met, but your sample size is quite large, right, over 30, then the results of the t-test are valid. So as long as we have large enough samples, we should be good. And the test statistic for a matched paired test is below. So we have the difference, right, x sub 1 minus x sub 2 for each pair. The sample mean of the difference, we call it d bar, but it's very similar how we found like the mean before. And then our standard deviation of the differences, again, very similar here. Our test statistic is very similar to what we saw with our t test statistic before. Note again, right, that n minus 1 is degrees of freedom. And we say, right, the difference is 0 in most cases. For our case, we're going to assume that assumption. Now note, the differences is always in the form x sub 1 minus x sub 2. But you need to define which time point represents x sub 1 and x sub 2. Based on what you want this difference to result in will depend if we use less than or greater than. If we want an overall negative difference, we will use that the difference is less than 0. So negative difference, less than, positive difference, we want greater than. And I'll talk a little bit more about this as we go through our first example in our next video.